5.3 we'll be putting together what you guys have been doing in 5.2, which was finding intervals where the function was either increasing or decreasing. Okay, and what we're going to do with that is we're going to pretty much take it one step further, and we're going to use where a function increases or decreases to find relative maximums or relative minimums. Okay, we call this the first derivative test. So 5.3, here's your heading. The main thing I want to talk about is the first derivative test. So at a critical point C, if f prime of x changes from positive to negative at C, then f of C is a relative maximum of f. Okay, and here you have a couple examples. We have this negative parabola looking function where so if this is a critical number, we'll call it critical number C. If it's increasing, that means that the derivative is positive, it's greater than 0. And then it switches to decreasing, meaning that the derivative is less than 0, then this must be a relative maximum. Okay, and it can look like this, where we have a cusp. Remember, that's where it's undefined, not the derivative is undefined. So increasing, cusp, decreasing. So that's the relative maximum. Okay. Likewise, we can use something very similar to find the relative minimum. If f prime of x changes from negative to positive at C, then f of C is a relative minimum of f. Okay, so here we have, now let's just switch it up to a positive looking parabola, or a positive function or parabola looking type of function. And now it's decreasing, so the derivative is less than 0. You hit your C value, your critical number, then you start to increase. This is a relative minimum. And again, you got the cusp, or the corner, like your book likes to call it. Decreasing, then increasing. This is your relative minimum. Now, if the signs don't change, so if f prime of x does not change signs at C, then f has no relative extreme value, no relative extreme value at C. Okay, a good example is the function y equals x cubed, okay, which I have here. So if this is a function y equals x cubed, you got that S or snake looking type of function, and you're increasing. Then at the origin, you hit a slope of 0, but then you keep on increasing, so it stayed positive. Then you don't have anything. You don't have a relative maximum or a relative minimum. Or a function that looks like this, where we are decreasing. You hit the cusp, but you continue to decrease after that. You don't have a relative maximum or a relative minimum there. So all of that was for your notes, just so you can have it in your notebook and have it as a reference. So hopefully you added that to your notes, and then we will continue with this example. So use the first derivative test to determine the local extreme values of the function. Remember that local extreme values, just talking about the relative extreme values. Your textbook just likes calling it local instead of relative. So step 1 is you obviously need to find your critical numbers. So let's start with find the derivative. So Cn for critical numbers. So we have f prime of x is equal to 3x squared plus 6x. So we have 3x squared plus 6x equals 0. Factor out a 3x, and we should get x plus 2 equals 0. So x equals 0, x equals negative 2. Okay, after that, just like in the last video, we will do the number line, but that number line should be for f prime of x, so f prime of x number line. So by the way, these are your critical numbers here, and those are the values that we're going to input on this number line. Let's do that. So we have negative 2, we got 0. So we have created some intervals. Remember that this function is a polynomial function x cubed plus 3x squared, so it's continuous everywhere. So this number line will go from negative infinity to positive infinity. So we have intervals from negative infinity to negative 2, negative 2 to 0, and then from 0 to positive infinity. Let's pick some test values, like, let's keep it simple, negative 3, negative 1, and positive 1. Okay, now what you guys are going to do is you guys will plug this in to the derivative. Remember that in this chapter we're looking at the slopes of the function. So we are going to be plugging it into the derivative. So what I want you guys to do right now is, again, pause the video. You definitely want to try this on your own first, and then I'll magically show you guys the answers in a bit. So pause the video right now, try this out. Okay, so hopefully you got these answers. Remember that we could care less about the actual value. The 9, we just care about the positive. We can care less about that. 3, we can care less about that. 9 also, we just care about the sign. It came out positive, it's increasing. It comes out negative, it's decreasing, and then it's increasing again. Another thing we can care less about is the critical numbers. After we've used them, we don't need them anymore. They don't magically become part of your interval. We are still only increasing from negative infinity to negative 2. So we have is something like this. And then we hit negative 2, we have a slope of 0 according to our critical number. Then it starts to decrease. Okay? So this is a relative maximum. Same thing, same idea here. It's decreasing. Then remember, if x equals 0 is a critical number, it's either undefined or 0 there. So the slope is 0, and then it starts to increase. This is a relative minimum. And your answer should look something like this. Okay? So relative maximum at negative 2, 4, relative minimum at 0, 0. And thanks to Desmos, we can easily see what the graph looks like. And there they are. Okay, so here's another example. Use the first derivative test to determine the local extreme values of the function. Here's your function, and what I want you guys to do is I want you guys to start it off. Step 1, go ahead and pause the video and find the critical numbers. Okay, so you guys do this right now, and then I'll show you the answers in a bit. So pause the video. So there it is. The critical number is x equals 2, x equals 0. Okay. Notice that I decided to skip the product rule by distributing. So once you distribute this, x to the 2/3, you have this function now. And I just took the derivative of that. Notice that this is not f prime of x. However, that next step is, now that's f prime of x. F prime of x, f prime of x. When I got to this third step, I have to multiply the top and the bottom by x to the 1/3 to get common denominators. That's how I got 5x over 3x to the 1/3 minus 10 over 3x to the 1/3, and pretty much this. And keep in mind that when the numerator is 0, we have the slope of 0. That's when the derivative is 0. When the denominator is 0, then that's when it's undefined. So at x equals 0, we probably have a cusp or a corner. Okay? Keep that in mind. Then you want to organize this in the number line. Go ahead and pick some test values. So we have intervals from -infinity to 0, from 0 to 2, and from 2 to +infinity. Go ahead and pick some test values and tell me where they're increasing, which intervals are increasing, which intervals are decreasing. Okay, pause the video. Okay, so check your answers with mine. I got increases from in the interval from -infinity to 0, decreases in the interval from 0 to 2, and increases in the interval from 2 to +infinity. Keep in mind, I do not care, I could care less about the test values. They were just used for exactly what I call them. Just to test them, that's it. So, if you notice, I did this without showing any work. You can do this in your head. Okay, 5 times the -1 is negative. Negative minus a negative is a negative over. And then 3 times -1 to the 1/3. That's the cube root of -1, which will still be -1. So it's a negative over a negative, which will produce a positive. Okay, here we have +5 minus 10. That's -5. All we care is that it's negative over a positive. Okay, the cube root of +1 is +1, and then times 3. So we get a negative. Okay, 15 minus 10 is positive over, again, a positive. The cube root of a positive value stays positive. So we have a positive over a positive, which is a positive. Okay, that's how I quickly got these values. So the relative maximum is 0 at x equals 0. The relative minimum is -3 radical, or the cube root of 4 at x equals 2. Plug this into the calculator. I got approximately, let's see, -4.762. Okay, and the graph is that. Okay, so there's that cusp I was telling you about earlier. Okay, and here we have the relative min, -4.762. Okay, and that is the end of this video.